My name is Emmanuel and I'm presenting the ADOPT system. ADOPT combines two powerful ideas in terms of data processing. The first one are worst-case optimal join algorithms. The second one is adaptive processing. Worst-case optimal join algorithms have been shown over the past years to perform significantly better than traditional join algorithms, in particular for cyclic queries, and adaptive processing leads to more robust optimization in scenarios where it is difficult to estimate the processing overheads of query plans before executing them, for instance, if the underlying data is skewed. So the hope of combining those two ideas is to obtain a system that performs well, in particular in scenarios where execution and optimization is challenging. Internally, ADOPT is based on the Leapfrog try-join, a popular worst-case optimal join algorithm. And given a query like the one that you see here, the Leapfrog try-join focuses on the join attributes. In this case, we have 3 join attributes, and for a given order of those join attributes, the algorithm proceeds by first selecting the lowest matching values for the first attribute, a value that appears in all relevant tables. Then it fixes that value and proceeds to the next attribute, and there finds the first matching value that is consistent with the currently selected value in the first attribute. After finding the value for the second attribute, the algorithm fixes that value and proceeds to the third attribute, where it iterates over all values that are consistent with the currently selected values in the first 2 attributes. After considering all those values, it backtracks and goes back to the second attribute, where it selects the next matching value still with the currently selected value in the first attribute. After that, again, it proceeds to the third attribute and iterates over matching values there before it backtracks again and ultimately backtracks back to the first attribute. So this is the high-level picture how the algorithm works, but a key decision in this context is the choice of an attribute order. And we have performed experiments showing that the attribute order has very significant impact on the performance. For instance, in this graph, you have execution time on the y-axis, and you have different attribute orders for the same query on the x-axis. And as you can see, you have a significant difference in terms of execution times between different orders. Now, traditionally, we would try to select one single order before query execution starts based on statistics about the data. But if data is skewed, for instance, it makes it very hard to reliably estimate the execution cost of potential attribute orders. And in those cases, you might make the wrong choice with a detrimental impact on performance. This is why ADOPT exploits adaptive processing in order to become more robust in cases where it is hard to accurately assess the processing overheads of query plans. This is the high-level picture of how ADOPT works. So for a given query, ADOPT performs a large number of episodes. Each episode typically just takes a couple of milliseconds. And within each episode, ADOPT selects an attribute order, then executes that order for a limited number of time steps, and finally evaluates the quality of that order. And from those quality measurements, it learns over the execution of a query to select better attribute orders. So it converges to optimal orders. And while it is doing all of that, it also produces a result tuples. Once it can guarantee that a complete result has been generated, execution of the current query terminates. A very important problem in this context is avoiding redundant work across different attribute orders. And in order to achieve that, ADOPT keeps track of unprocessed parts of the search space for join results. And then in each episode, it restricts the scope of the Leapfrog try-join to a limited number of values for each attribute. It keeps track of which scopes have already been processed and makes sure that the Leapfrog try-join algorithm is only applied for value ranges that have not been processed previously. Now we can apply the same technique that we use to avoid redundant work across different episodes, to also avoid redundant work across different threads. So Adopt supports multi-threading, and it makes sure that the same values are not generated neither by different threads nor with different attribute orders. Now, a key problem in this context is making sure that we select the right scopes that have not been processed yet. Let me illustrate the principle by an example. So the components that are concerned by the technique that I'm about to present are the ones that are marked up in red. So the goal is to select unprocessed scopes for each thread and in each episode, and after each episode to remove processed parts of the search space. Now let's assume that we are processing the query from before. It has 3 attributes which are represented on the x-axis, and the values for those attributes are represented on the y-axis. What is marked up in red are the last values considered by the leapfrog try join before the current episode ends. And to make things simple, let's assume that the algorithm has started from the lowest value in each attribute. Now the question is, after processing a certain number of value combinations, which scopes remain unprocessed? In order to determine that, it is useful to remember a couple of key properties of the leapfrog try join. First of all, the leapfrog try join considers values for the same attribute in ascending order. And secondly, the leapfrog try join only backtracks to a previous attribute after it has processed all value combinations for the current attribute. Now, based on those two key properties, we can first of all say that for the currently selected values in the first 2 attributes, the algorithm has not yet considered the highest possible value for the last attribute. So that corresponds to a scope that fixes the values 5, 3, and 5 for those 3 attributes. Also, if I look at the second attribute, I know that the algorithm has not yet processed any value higher than the currently selected value for the second attribute for the currently selected value in the first attribute. So those parts marked up in blue correspond to scopes that have not been processed yet and that would be eligible for processing in the coming episodes. Now, I mentioned that Adopt converges to optimal attribute orders over the execution of a single query. So let's discuss in more detail how it actually accomplishes that. In order to converge to optimal orders, we first of all need to be able to recognize optimal orders via quality measurements. So this concerns the component that is marked up in red. I'm going to discuss first how we measure quality, then I'm going to discuss how we select attribute orders based on those quality measurements. Fortunately, we can use a similar principle to the one that we have used in order to determine unprocessed scopes. Given the same situation as before, we now want to recognize which scopes have been processed in the current episode. And again, due to the properties of the leapfrog try join, we can say that for the currently selected values in the first 2 attributes, the algorithm has considered everything up to the currently selected value in the last attribute. Also, when considering the value selected for the first attribute, we know that the algorithm has considered all possible value combinations for every value in the second attribute before the currently selected one. And then finally, for the first attribute, the algorithm has considered all values before the current one, and for those values it has considered all possible value combinations for the remaining attributes due to the second property of the algorithm. Now we have calculated the scopes that the algorithm has explored during a single episode, and based on that I can calculate a volume in terms of the number of value combinations that the algorithm has explored in the current episode. So here I only need to multiply the number of values considered for each of the 3 attributes. I can use the number of value combinations explored per time unit as a measure of quality, because ultimately, in order to finish query execution, the algorithm needs to consider all possible combinations of values. So if it can do that faster, it will terminate faster. Now, if I have those quality measurements, of course they will be noisy because data is not perfectly homogeneous. So even for a fixed attribute order, it will sometimes measure more progress and sometimes measure less progress for the same number of computational steps. So the adopt system needs to iteratively select attribute orders to try out in episodes. And now it has a choice between selecting attribute orders that are similar to attribute orders that we have selected previously, which seem to work well. But if you only keep doing this, we will probably get stuck in local optima, and that is inefficient. So every once in a while, we need to try out attribute orders that are very different from the ones that we have seen so far, and that is also called exploration. And of course, there's a tension between those two, exploration and exploitation, also called the exploration-exploitation dilemma. And the most principled way to resolve this dilemma is by the application of a reinforcement learning approach. And in reinforcement learning, we generally have an agent that interacts with an environment. It can influence the environment via actions, and it obtains rewards from the environment that it tries to maximize. But initially, the agent does not know how to do that. Reinforcement learning algorithms, they provide a principled framework to deal with this uncertainty. Now, in this specific scenario, the agent, that is of course the adopt system, the environment is characterized by query and data properties, and actions are associated with selecting an attribute order and trying it out. Rewards are associated with the volume in terms of the value combinations that we have processed so far. In the experiments, we compare adopt against the various baselines. Here are some key results from our evaluation. We are comparing against mature database systems like PostgreSQL and MongoDB, as well as against SkinnerDB, which is a system that uses adaptive processing and reinforcement learning as well. We also compare against two baselines that use a worst-case optimal join algorithms, empty-headed, and a commercial system that features worst-case optimal joins. We compare the systems on a variety of benchmarks, and those include benchmarks that focus on cyclic queries as well as other benchmarks. They also include benchmarks that have skewed, some of them even highly skewed data, making a priori optimization hard, as well as other benchmarks like TPCH that use synthetic data, which is uniform. And it turns out that adopt performs particularly well for those benchmarks that are hard in terms of the queries, meaning cyclic queries, and are hard in terms of optimization, meaning that we execute on skewed data. Also, if data is highly skewed, for instance, for the JCCH benchmark, adopt performs best among all compared baselines. So in summary, adopt is a system that combines worst-case optimal join algorithms with adaptive processing, and that enables it to perform well, in particular in scenarios where you have cyclic queries and skewed data. The code is available, and now I look forward to your questions.